Good morning, everyone, and welcome to today's webinar, Collaborative Robots Technology, Selecting the Right Cobot for Your Application. My name is Nur Farhana, and I will be your MC for today. We appreciate all of you for taking your time off your busy schedule to join us today, and we hope you will find this webinar fruitful and engaging. Without further ado, to begin this webinar, it is my pleasure to introduce our speaker for today, Mr. Vincent Hoy, Key Account Manager from APulsar Technologies, Sdn Bhd. Without further ado, I would like to pass the floor to Mr. Vincent.
All right, thank you very much, Farhana. One moment, let me bring my slide up. Okay, Farhana, can I double check for me? Is my slide visible?
Yes, we can see your slide.
All right, so thank you, Farhana. So good morning, everyone. My name is Vincent, and I am very happy to be able to conduct this webinar to all of you. First of all, I would like to thank the team from FMM for conducting this webinar, organizing and conducting this webinar. And I would also like to thank each and every one of those who are attending this webinar for spending your time. And I hope that by the end of this presentation, I will be able to impart upon some valuable knowledge or some valuable insights in terms of the collaborative technologies. A little bit of background. I have spent the past 8 to 9 years dealing with industrial robots and collaborative robots in the manufacturing settings. And I hope that I can be able to share some of the insights from all these years of learnings to assist everyone in advancing their manufacturing technologies, especially in Malaysia. So without further ado, let us begin. This is the very quick agenda that we will have for the presentation today. We will start by sharing with you the first generation of collaborative robots, followed on by the evolution on the second generation of collaborative robots. Next, we will talk about a no-collision safety technologies that can be used in robots. And then they're going to follow up by impedance-controlled robots, which is something that is quite new. And they're going to discuss the practical applications and the case studies and see in what circumstance would the different generations of collaborative robots be more suitable. And we will end the entire presentation with a Q&A session. So with that out of the way, I would like to first start with a general technological disclaimer. Now, I'm going to first show you 4 photos over here. These are photos of the gearbox within the industrial robots, and these are really established brands. You can see here there is KUKA, there is ABB, Fanuc, and Yaskawa. And you might be wondering why I bring up these photos. It's because I want you to notice how different the entire gearbox setup is within each of these well-known industrial robot brands. Because I want everyone to understand that throughout this presentation, I want everyone to keep in mind that different manufacturers have different internal mechanisms and designs to achieve the performance of the robots. And the same is true for collaborative robots. Unfortunately, they don't have really nice pictures of the gearbox of all the different collaborative robots, so I'm not able to show it out in detail, but keep this in mind. And second thing is that the following sharing, the information that I'm about to share is actually very general and it's a broad classifications of the technologies in the collaborative robots itself. So you may compare multiple brands and you will say that they have the same performance, they may have the same repeatability, they may have the same movement and joint angle, but there is a good chance that in the robot design itself, the mechanisms are totally different, right? So in this presentation, I will just try to group them in a very general manner so that we can be able to use this information when we are designing for our automation projects in the future. In fact, for most of us, if we look at the robots from the outside, we can't really see the difference, you know. I give you an analogy. For those of you who know about Formula One, the racing car, right? You may look at the 20 cars on the track and they all look the same, you know, 4 wheels, a front wing, driver sitting in the center. But when you are familiar with the industry or when you're familiar with the technologies itself, you will begin to notice subtle differences between the cars. And the same thing is true with all the collaborative robots. Each of them may look the same, but they are actually subtle differences which differentiates the brand between each other. So with this disclaimer done, we shall now move on to a very quick refresher of what is the main difference, the advantages and disadvantages of collaborative robots in general. So a collaborative robot is designed to work safely alongside humans in a shared workspace or a shared environment. That was the key differentiator that differentiates it from the industrial robots. So generally, the advantages of collaborative robots, there are four. First is in terms of safety. You can work with the humans and the robot without requiring safety fencing to isolate the machine from the operators. Second, in terms of programming, collaborative robots, they tend to take a more user-friendly approach, a more graphical programming approach, a simpler programming interface as compared to the industrial robots. Number three, collaborative robots are much easier to set up due to their lightweight. In terms of the robot is lightweight, and the robot's controller is also significantly smaller. So in the past, when we want to install an industrial robot, one person cannot do it because you have to move this big robot controller cabinets around. But for collaborative robots, there is an opportunity where one person alone could be able to set up the entire robot from the controller to setting up the robot on the robot base and even the application itself. And because of the lightweight design of the cobots, it makes it more flexible to mount. The same model of the cobots can be mounted table mounts, inverted mount, wall mount. Whereas for industrial robots, if you want to do inverted mounting, you have to select a model that is designed for inverted mounting. So this kind of flexibility is one of the key advantages of collaborative robots. Now, in terms of disadvantages, there are also four. First is in terms of the payload. Now, because cobots, they want to really prioritize on the safety to be able to work side by side with humans, they sacrifice a number of things, the speed and the payload. So if you notice, for most cobots, right now, they rarely go above 30 kilogram payload, whereas for industrial robots, you can go up to 1 ton or even 2 tons of payload. Also, in terms of speed, there are many industrial robots that can operate at a much faster speed compared to collaborative robots. Again, this is because of safety reason. If the robot moves too fast and it hits an operator, it will hit it very hard, and there will be quite a heavy injury onto the operator. So collaborative robots, they tend to be much slower and they slow down a little bit because of the safety factor. Three, in terms of robustness, basically, you don't expect to put a collaborative robot in a very harsh, hot, and dusty environment. Imagine a steel plant, you have molten metals, very high temperatures. This is where industrial robots excel because it is built with that robustness in mind and it can be able to survive in that harsh environment. And finally, in terms of repeatability, I would say that the industrial robots are much more precise in terms of their accuracy and their repeatability. In fact, the industry benchmark, I believe, is about 5 microns for industrial robots and about 20 microns for collaborative robots. So it's about a 4 times improvement if you compare cobots and industrial robots. So this is the general, very brief overview between collaborative robots and industrial robots. So now let's talk about the first generation of cobots and what is interesting about it. So this technology actually applies with the first collaborative robots being launched in the markets from the early 2010s. And it goes on all the way until the late 2010s or the early 2020s, right? So what is interesting is that The first generation of the collaborative robots, when they build and design it, the main goal really is just to work alongside humans. They can sacrifice the speed, they sacrifice the payload, they sacrifice the accuracy so that they can work alongside humans, because that is the key product differentiator between cobots and industrial robots, right? So therefore, some of the key features that they emphasize are, number one, you can use this robot without safety fencing. And even without safety fencing, you are still compliant with the safety standards. Number three, they program the robot such that it is very user-friendly. It has a very user-friendly user interface for operators and technicians to be able to program and adjust the robots. And the last selling point is what we call the hand drag point teaching. So every time you see these presentations from many and all these collaborative robot brands, they will always emphasize that you can use your hand to drag the robot around in order to teach the robot points. So as you can see here, these are all the brands and their respective series, which are considered the first generation of this collaborative robot. The pioneer of it all is, of course, the Universal Robot with their UR5, specifically their CB3 series now. So, of course, every other brand here that is listed here and their respective series, these are actually robots that are using the first generation of the braking technology. So the key point here is that they use something called an impact pin brake design. So I'm going to explain a little bit more what this is all about. Now, what is an impact pin brake? Let me show you this diagram. So an impact pin has what's called a strike pin over here and a latching fin on this side. So all this slot here are the latching fins. Of course, there are many different types of designs, but the concept is the following. Number one, when the robot is powered off, right, this strike pin will be used to clamp on this fin component here so that the robot does not drop down, like collapse totally. But since there is a little bit of gap between these two areas, the pin cannot close the gap quick enough, right? So sometimes you will be able to see that the robot will drop a certain height, especially in collision status or in e-stop status. And this height drops can be between about 5 to 10 mm. Some robot manufacturers, their height drop is not really noticeable. Some is more noticeable, but generally this is the range. And the key thing is that even though the robot has dropped in terms of the height, this does not affect the teaching point or the accuracy of the robots. And this only happens during the robot power on and off cycle, during the e-stop when somebody pressed the e-stop button, during when it detects a collision with an object, or when we are enabling or disabling the robot. So for those of you who are already using robots for several years, using the collaborative robots for several years, you would notice this, right? In fact, let me show you a video of how it is. So you can see right now, this robot is programmed to move a straight line. So you can see now it can move very accurately without any problem. But now as we get ready to press the e-stop, and when we press the e-stop, you can see the robot's pin actually sink into the plastic here. So this actually demonstrates this is using the strike pin technology, where if you press the e-stop, the robot will actually drop in a little bit. Now you can see this video, we are going to reset the robot. We are going to move it into a safe position and replay the program. And you will notice that when we replay this program, the robot actually does not lose any accuracy. It still can run the same program with the same precision. It's only when we press the e-stop that the robot will fall in about 5 to 10 mm. So this is the key defining technology of the first generation of collaborative robots. Now let us talk about the second generation. So the second generation of cobots, they begin to appear in the early 2020s. And in fact, right now, most of the branded collaborative robot suppliers, they are actively pushing the newer series of cobots, and these are generally second generation cobots. Okay, so the goal of the second generation, they wanted to improve in terms of the performance and the features from the first generation of cobots. So they already get the basics right. Yes, the first gen cobots can work with the human. Now they want to make it have a higher performance, higher speed, and even better features. So this type of new second generation cobots, what they emphasize on? They emphasize on faster joint speed on all joints. They use a stronger motor with the similar features. They also have a greater range of motions from all joints. In the past, first generation cobots, joint 4, 5, and 6 may have limited rotation, but in the second generation, they have a greater joint rotation. Another point is that they now have even greater flexibility in terms of the programming user interface. In first generation cobots, they usually would choose either graphical or scripting. But in the second generation, we can do graphical and scripting. You can choose which mode of programming you want, so it gives you even greater flexibility. And of course, they further enhance the safety features by having more sensitivity tuning, more safety IOs in the controller side. So some examples of these second generation collaborative robots would be this UR7E, or in general, the E series. And then for the TM or Omron, they have the TMS series. And for Dobot, they are the CRA series. So all these three, they are more of the second generation with the newer features. And the key defining technological differentiator is that they now change the brake design. Instead of an impact pin, they now use an electromagnetic brake design. So now we will explain a little bit more about this electromagnetic brake design, what makes it so different. Now, this diagram is a very general concept of the electromagnetic brake. You have the motor rotors, you have the joint components, the mounting base, and the braking armature here to hold the robots together. So when the robot is powered off, the brake body and the braking armature, right, they will engage within less than 20 milliseconds. So now it becomes very, very fast response. In first generation, they wait for the pin, the impact pin, to drop. So it's a mechanical trigger, but now it becomes an electrical trigger to stop the robot. And because of the fast response time, the robot drop height now, it's become less than 1 millimeter. Actually, it's barely noticeable, right? And because of this, again, when the robot brake is engaged, it does not affect the teaching point or the accuracy of the robot. And the same situation occurs. This will occur during the robot power on and off. It will also occur during e-stop, collision, and also when we enable or disable the robot. So in summary, the second generation uses the newer technology, this electromagnetic brake, and you no longer see the behavior where when you press e-stop, the robot will drop down. In fact, we can show you this video. So now you can see the robot is moving in a straight line. And now when we press the e-stop, you will not notice the robot will drop. Whereas in the first generation of Cobot, when we press the e-stop, the robot will drop ever so slightly, about 5 to 10 mm. It may touch the box in this scenario. Okay, so now let's do a very quick summary of the comparison between first gen and second gen collaborative robots. The key differentiator being, first gen, they use the impact pin brake design. Second gen, they use the electromagnetic brake design. Next, for first generation, they tend to have a slower joint speed, and they also have a limited joint motion range. For second generation, they improve upon it. They have the faster joint speed, and they have a greater joint range for some of the axes of the robots. Next, for first generation cobots, they have a limited programming interface. Usually it's graphical or script. My understanding is that universal robots they are script, and for TM Omron, they used to be purely graphical. But in the second generation Cobot, it tends to be more flexible. Right now, people begin to offer both graphical and script. So it gives you more flexibility for the programmer. Next, for first generation Cobot, their payload tends to be less than 20 kilograms. Because at that time when they were designing this robot, they are just trying to make sure that the robot can work safely with the humans. And usually the greater the payload, the greater the risk to the operators, especially when a collision has occurred. But for second generation, they improved upon their safety algorithms, they improved upon their motor technology that they use. So the payload has increased, and now I think it can go up to 30 kilograms. And finally, in terms of cost, now, today in 2026, first generation cobots, they tend to be a little bit cheaper because they are using a slightly older technology. Whereas for the second generation collaborative robots, it tends to be slightly higher cost because they are using the newer, more advanced technologies, right? So this is a very general, very broad comparison between the two generations. And now we shall move on to the next topic, which is a no collision cobot safety technology. Now, first things first, we can all agree that as manufacturers, right, safety is the top priority in the manufacturing line. In fact, that is the whole selling point of collaborative robots. It's safer to be used in the manufacturing line. It's more user-friendly for the operators. Now, however, for almost all collaborative robots, right, the robot must hit something first, only it can detect a collision. Even if it's safe, it still has to hit something, whether it's an object or a human or an operator in the operations. Only then it will stop, right? Some operators, they said, or some of the robot brands, they said, oh, we can tune the sensitivity of this collision to the point where even a simple touch with your hand would be enough to trigger the robot to stop. That is true, but the fact remains, it still needs to touch something, only then it can stop. And this still creates a risk sometimes for humans, where you might get some minor injuries, especially when it is the robot gripper that hits the operator, or when it hits the operator and the load that is carrying drops, or the load itself contains sharp edges. One of my customers, he used to tell me, he says, especially the safety officer, he says that, all robots is dangerous and must be put into safety fencing, no matter if you are cobot or industrial robot. And I asked him why. He says, very simple. You imagine the robot, you put a knife at the end of the robot as an end effector, and even if it's a collaborative robot, if you take the knife, it stabs into somebody, then it stops. But the fact is it still stabbed into somebody. So that's why it failed in terms of the safety compliance. And when he gave this kind of example, I think, yeah, quite interesting. So we will try to think of what other methods that we can use, to create an environment where there is no collision at all, no touching at all, and we can be able to still maintain the safety for the operators. So there are two ways. First, the very traditional method, something that has been applied in manufacturing lines for quite many years already, is that we use a safety scanner. We use this type of safety scanners. So one of the advantages, right, is that we can define the safety zones to change the robot's speed. So in this case, we can use the safety scanner. We can define, let's say, yellow zone here. So if any object is in the yellow zone, the robot can slow down. Maybe instead of running at 100% speed, It can run at 50% or 30%. You can define the parameters. And you can then define the red zone, where if any operators or any humans walk into the red zone, you can ask the robot to stop completely. So this is how we have been doing no collision safety implementation for many years. Now, the advantages of this system, there are a few. Number one, we can customize the safety zone. So you can see normally for safety scanners, they always come in a circular area. But for some safety scanners, you can define it to be a square or a rectangle, or you can even define multiple safety areas and safety zones. So it's very customizable. Second, it totally eliminates safety fencing, even for industrial robots. So then you can definitely save some space and you can save some cost, and it makes it easier for your technicians to perform maintenance. And lastly, it can definitely prevent human accidents because you have already defined the zone so well. And when anything or anyone goes into the red zone, the robot stops completely. So you can almost eliminate any risk of accidents. However, the disadvantages of using this method is that, number one, you have higher additional costs and you need to perform some additional integration because you have to purchase these kinds of safety sensors, and these things are not cheap. And you have to program it, you have to define the safety zones, and then you have to define the interlocking between the sensors and your robots and your process. Some may question, is it the red zone here is equivalent to an e-stop? Sometimes when we do an e-stop for your entire manufacturing line, you have to reset the entire production sequence, and that's very tedious. Some manufacturers say that the red zone is only to stop the robot, but does not stop the production line. So you see, you have to think of all this process engineering, when you implement this safety scanner. Next, this type of safety scanner is not really feasible in a highly dynamic environment. So imagine if in this space here, or in this space, you always have objects moving in and out, or you are always changing the machine layouts, or sometimes you will put the incoming material here, outgoing material here. So your environment is always changing, right? Then it's not very suitable to use safety scanner because it's very difficult to cater for all these changes. Sometimes somebody misplaced an object in the red zone here, and then your whole line is not running and you have no idea why. Then you have to go and find out, oh, somebody placed an object over there. So that kind of environment is tough to implement this kinds of safety scanner. Next is that when a human goes into the red zone, we would usually program the robot to stop completely. So this means that if a human operator needs to go in to do some minor adjustments, the production line will stop. Some may say that this is good for safety. Some may wish that the robot can continue to do some other processes while the human is working on another process. So these are the challenges when we want to implement this safety scanner. So the second method, this is a newer technology. The second method for us to do this, I'll show you this video. This is safe skin technology. It's pioneered by Dobot brand. And as you can see here, the Cobot is able to detect human without touching it, right? They put some special sensor on it, and that even before touching, the Cobot will be able to detect and stop. Yeah. So this is something interesting, another way for the robot to stop itself before it touch or any accidents occur, right? So now let's talk more about this. This is a safe skin technology. It's pioneered by Dobot. So what are the key features? First thing, it uses an electromagnetic induction sensor that is wrapped around joint 4, 5, and 6, designed for human skin. So here is joint 6, here is joint 4 or 5, and here is joint 4. So as you watch in the video, this joint 4, 5, and 6, instead of the hard metal exterior, is actually made of this soft silicone cover that not only detects, but it also serves as a padding or if it indeed hits something. Now, the advantages of using this kind of technology is that, number one, it enables the robot to work very closely with human. Means that, like you can see in this picture, the little girl can literally walk next to the robot. And if she is nowhere close to the end effector, the joint 4, 5, and 6, the robot will keep doing its job without any disturbances. Second thing is that this kind of technology is quite resistant to external environment interference. So imagine if you use the previous solution, the safety light curtain. Imagine if there is a change in external environment, suddenly the light change lah, they put the different objects in different locations, that would disrupt the operations of the machine. But for this technology, because the detection is only at the end effector near joint 4, 5, and 6, the chances of external environment interfering with it is much, much lesser. And next, it has a very fast response speed, 10 milliseconds, and the robot would be able to stop. And we can tune the sensing range up to 15 centimeters. Means that if you can tune it to be 5 centimeter all the way to 15 centimeters. And the best thing is that this technology is built into the robot. I cannot buy this as an additional accessory once my robot is there. So this thing is built in the robot, in the factory, and shipped together. And this also means that the software is fully integrated. I just have to enable and disable this function. So I don't have to go through all the hassle of programming it, testing it, integrating it all together. Now, the disadvantages of this thing. One, it has limited coverage. It's only installed in the joint 4, 5, and 6, right? So some may say, oh, joint 1, 2, and 3, how? If let's say joint 1, 2, and 3, will it still hit somebody? The answer is yes, it will still hit somebody in joint 1, 2, and 3 if they're not careful. And next, it may limit the robot motion in tight spaces. So as you can see in the video just now, right, if let's say there is an object too close to the robot, the sensor itself may detect the object and it may trigger itself to stop. So imagine if you are in a very tight space environment, right, then this type of add-on, this type of safe skin technology is not very suitable. Okay, so these are the no collision Cobot safety technologies. I saw that there are a number of questions coming in. I will answer the questions at the end of the presentation. I will address them one by one. All right. So now let's move on to the next topic. Now this is very interesting because this is very new and the market is not very familiar with this yet. And that's called an impedance-controlled collaborative robot. Okay. So what makes this robot special? The key concept is that this robot is designed to regulate between the robot's position and the external force being applied to the robot. Now, three things. One, this robot mimics a mass spring damper system. Later, I will show you a video and you will be able to see exactly the behavior of this robot. This robot uses a lot more force torque sensors and torque controlled actuators to control the motion of the robot. And thirdly, this robot actually yields to external force but maintains the end position. Means that you can actually push the robot around like it's like jelly, So then you can do some pretty interesting applications. Now I show you this video so you can see this robot, human hand, you can push the robot, it can move like a jelly, you can move it around, right? And the key thing is that after you release the external force, the robot will always try to maintain the position that you have teach the robot. So he will always try to maintain that position. So let's say you see now, he will push the robot away. Then once he releases the force, the robot will bounce back to the point that you have teach it. In fact, you can even twist the robot's other joints around, and as long as it can maintain the final position, the robot will be able to adapt to this environment. So you can see now he pushed the other joints, he pushed it to the other extreme end, and the robot will still maintain the position here, right? So they call this positional compliance, whereby no matter how much external force you exert to it, the robot will always try to come back to the position. Now, what is the key advantages of these types of impedance robots? There are four. First, their safety is much more superior compared to our standard collaborative robots. Why? Because when it detects a force, let's say it hits something accidentally, rather than triggering e-stop, the robot actually bends around, it gives way to the touch. So it can actually bend around the obstacle, right? So when we are operating together with a human, and if let's say the robot is moving to where the human is, the human can actually push the robot aside and continue to do their job, and the robot will not lose its position, and it will also not trigger an emergency stop or an error for the robot. So in this case, it's very superior in terms of safety. I will give you an example. If I'm using a Cobot, and if the Cobot hits my hand, right, I can set the sensitivity such that I don't get hurt, okay? I don't get hurt. But my Cobot will stop. It will trigger emergency stop, collision detected. And then I have to go and reset the robot. But with this kind of impedance controlled robots, right? When the robot hits me, the robot will just wait and he will bend a bit. I mean, he will wait, soft touch until my hand is removed. Then he will continue to move to the position that we program it to be. So in that case, it's much more superior in terms of safety. Second, it can do adaptive tasks much better. Because this robot, it can feel its way, it can feel the object as we teach it. So it makes it much easier to adapt to irregular objects or irregular positions. And next, it can easily compensate for misalignment. So in the past, every time we want to do the insertion, like imagine a hole and you want to insert something in the hole, this type of application, we always say to the manufacturers, you must pair together with a vision inspection system or a sensor, because we want to measure whether there's any misalignment, and then we would program the robot position to compensate for the misalignment. But for this type of impedance robot, right, it's very interesting because it can feel the object, and like a human, you can slowly adjust your way to fit into the hole. Later, I will have some videos to demonstrate this a very unique property of this type of robots. And lastly is that it has a very consistent force regulation. So for applications such as polishing, sanding, grinding, these are very challenging applications because every time we have a flat surface and we want to polish, it's relatively easy. We can put a force torque sensor on the robot, on the 6-axis of the robot. So you press down, it can push at a consistent force. But this is easy if you have a flat surface or a slightly curved surface. But when it comes to surfaces that are very wavy or those that has a very complex contouring, right? This type of robot is perfect because it can feel its way throughout the entire robot to make sure that you have a very even and very beautiful polishing or sanding, right? So this is a very brief description of this newer technology of collaborative robots. So let's go on to some of the practical applications and case studies. Now, the goal for every automation project, or even for myself, is that I want to make sure that we are all able to leverage on the features and strengths of the different generations of collaborative robots to achieve the application that you want. So in this example, in this video, if we are to do a basic pick and place, vision inspection, basic assembly, actually, first generation collaborative robots is enough. Why? Because you only need the basic robot motion and function, right? You don't need some fancy applications. You don't need some fancy solutions. Provided that there are no challenging requirements on the process or the parts of the jigs, then you can be able to use this first gen. Why? Because your priority is you want to have the lowest cost possible to achieve your ROI. Remember, I shared that for the first generation cobots, they tend to be a bit lower cost. Today, they tend to be a bit lower cost because they are using the older technology. Okay. So another example application would be for palletizing in general. Now, palletizing in general, most of the solutions you see out there that they give the full palletizing solutions together with the robot and the pallets, right? Usually, they tend to be first generation collaborative robots. Why? Because palletizing is a very price competitive applications. You can now find so many suppliers from so many different brands. Everyone can give extremely good pricing. And it's all because they are using the first gen, the older technology of cobots, and it's good enough to solve the problems, right? And this is especially if you are handling non-fragile parts. You don't even care. You just want the robot to pick and place nicely, and it does the job, and that's it. The key here is that you always want to balance the system speed and the system cost to achieve your ROI. Some people may say that palletizing is not suitable for cobots at all. You might as well use industrial robots because they are much faster, they can carry for a much higher payload. And that is true to a certain extent. It really depends on how big is the box that you're handling, how fast is the output from your conveyor line. If you have very high throughput from your conveyor line, Cobot is definitely not fast enough to cater for your application. But if your throughput is not very high and you want something cheap to start with without safety fencing, without all these complex interlocking systems, then a collaborative robot palletizing is the perfect solution. Next one. Now, this is quite interesting, this application where you are using the robot to paint a building. This is an example of a video in China because they build high rises really fast, right? And in order for them to save on the labor cost and the labor time, they actually use robots on an AMR system to move around the building to very quickly spray paint all these walls. So for this application, definitely hands down, first gen is the answer. Why? Accuracy and repeatability is not critical since your paint will be overlapping anyways, and there are some portions which at the bottom here you have to manually paint it. So it's not really mission critical. So first gen, good enough. And it is very unlikely for you to damage the spraying head in an e-stop scenario. So you recall in the beginning, I mentioned that if you press the e-stop, the robot will drop a little bit. So in this scenario, there is so much space on the floor. Even if you press the e-stop, the robot drops a little, no chance of damaging your spray or your spraying head. So you want to optimize for the lowest cost possible, and that's where the first generation robot is the most suitable one. Now, let's talk about this application. Medical and chemical lab automation. For this type of applications, I would highly recommend for you to consider second generation Cobot and above. Why? Because you are dealing with fragile materials and very fragile samples. And that, because you are this type of machines, lab equipment, the space constraint is very critical. So you want to make sure that your robot has the most flexibility in terms of the joint motions and the angles. Now, why I say that when dealing with fragile materials, better to use second generation Cobot? Because you imagine if the robot is picking up a test tube from a tray, right? It's picking up, and before it fully left the tray, somebody pressed an e-stop or something triggers the e-stop. If I use the first generation Cobot, the Cobot will drop, and that may actually break the test tube, or it may actually break the medical samples, and that's something we want to avoid because medical environment, we want to make sure that all the samples are well processed. So that is why second generation is more suitable. Another example would be for welding. So for welding, our second generation Cobot will be most suitable because the welding gun will not be damaged when you press the robot e-stop during this welding process. So you imagine during the welding process, the welding gun is very near to the metal pit, the workpiece that you're working with. And if let's say it's welding halfway, suddenly you trigger the e-stop, the whole welding gun will drop about like 5 to 10 millimeters. And sometimes that would be the distance between the workpiece and the welding gun itself. So that may actually cause the welding gun to touch the workpiece or bang the workpiece, and that may cause your welding gun to be misaligned. So this is one of the issues. And second thing is that for production environments that have high mix, high volume, high mix production where you have to always change new models, right? Collaborative robots is much easier to teach the welding patterns for new products. But of course, if you compare with industrial robot, it cannot defeat industrial robot in terms of the speed. So for productions with high volume, I would think that industrial robot is the better solution. But for manufacturing that have high mix, then collaborative robots may be more suitable in this scenario. Right, next, CNC machine bending. So you can see in this video is a good example of how you can use safe skin technology to collaborate with the humans and the machine itself. So in this video, right, we can use second generation because we do not want the Cobot to drop when it is loading and unloading the materials into the CNC machine. At the same time, if your process requires the manual parts loading or manual parts handling by operator in this case, so by using the safe skin technology, right, the operator can be able and be very confident they know they can put their hand to go and move some parts, even though the robot is very close by, because the safe skin can detect their presence and stop so that they can do their post-processing. Then only the robot continues to continue their process. The key advantage of using this is that you notice how even after the operator removes his hand, right, the robot continues the program sequence. So I don't have to restart and reinitiate or press the start button for the robot to continue. It can just continue the program without any interruptions. Now, let's move to this application now. This is very interesting, advanced parts insertion. This is something that impedance Cobot is really, really good at, especially if your incoming parts is not consistent. So if you see in this video, you notice the parts here and the position of the robot is not aligned. And if I were to force it, it will create a collision. But this type of robot, because it can feel the hole, it can actually adjust up and down a little bit without us needing to program this feature. So he can be able to very safely and easily slot in these kinds of applications, right? A lot of the times when I meet customers and when I propose the applications, I always tell them, if you want to use robots, you must give me a consistent incoming parts. Then only I can consistently assemble for you. But oftentimes to create that consistency is very difficult. Like in this scenario, the parts is just moving on an open conveyor. You can even see the parts shaking as the conveyor stops. And the position may not be even very fixed. So this is where the impedance Cobot is really, really thriving in this kind of environment. I cannot do this with normal collaborative robots unless I put a vision system just to check whether there's any misalignment or not. So that is an additional cost for me. Now, another application we can talk about is glue application, right? So sometimes when we want to do gluing for simple applications whereby I just have to glue a straight line, glue in a rectangular or following the frame shape, that can be done by any robot. But if let's say in an example where I need to apply the glue around this tip, you see around this circular area, wow, this is very, very challenging, especially if this object here has a bit of free play, means that it can jiggle around. So how to mimic human operator, they can take the brush, right, and then they can brush around this tip very nicely. This is where impedance cobot can utilize their force control and their ability to feel the object to brush around it. So this is something very unique that is very interesting that you can that a lot of the times many of the robots are unable to do it well, and this is something that impedance cobot can do. And last but not least, I show you one last example. This is inserting the testing device to test the electronics, right? So in this case, you see in the video, the robot can actually feel, you see he can pick up and then he place it in, he cannot go in, but he can jiggle around and he can find the correct positioning, then only he can slot in the testing things into the devices very nicely. So you see, in this type of applications, I've known of several cases where the customers requested to use robots, to do these kinds of USB insertion. But a lot of these projects fail because when we use the traditional collaborative robots or even industrial robots, they don't have the ability to wiggle around to fit in these parts, just like humans do. So this is where the impedance cobots really shines. You see, especially here, you can wiggle around to find the correct hole to go into. So this is really his key advantage, right? So that's all of the applications and case studies that I would want to share for today. In fact, that is the end of the presentation, and I hope that all this sharing and case studies will be very useful. It gives you some ideas of what are the challenges and how can we go through the selection of the products to match what is required in your manufacturing line, right? So now we shall move on to the questions and answers session. Farhana, will you be assisting me with the questions?
Yes, Mr. Vincent. Okay. Sorry for the error. Okay, we will now begin with the Q&A sessions, but before that, I would like to remind all participants to please kindly complete the feedback form by scan the QR code as displayed in the slide. And also you may click the link that is being shared in the chat box. Once you do so, the presenter today will be able to share his presentation documents to you. Now we're going to begin with the questions in the Q&A box. Okay, from Sue Chong. May I know the price of the Cobot brake technology?
Well, in terms of the specific price of the brake itself, there actually is not stated. But normally, if we compare the first generation and second generation Cobot, usually, very broadly, price difference is about 10 to 15% between the two generations.
Thank you, Mr. Vincent. Moving on, is there any government subsidy available, for instance, from MIDA for the purchase of this Cobot?
All right, thank you for the question. I believe FMM will have a lot more context, when it comes to these kinds of grants and subsidies for automations projects. So perhaps we can discuss this further to see how we can collaborate to move on this manufacturing line improvement.
Thank you, Mr. Vincent. Okay, moving on. If the machine encounters any issues, what kind of qualified personnel would I need to hire to handle maintenance or troubleshooting?
Okay, thank you for this question. Now, this question is a bit tricky to answer because when the machine encounters issue, the first question we have to identify is this issue related to the overall machine or is just related to the collaborative or the cobots itself? Right? Because a lot of the times the cobots, when you buy the collaborative robots, they don't come alone. They usually come in a full machine for it to perform a particular process. So if let's say it's the machine issue, then definitely you need to hire someone who is able to handle your PLC, your sensors troubleshooting, your process troubleshooting. So usually that's where the maintenance engineer or this process engineer will be very familiar with. Now, if we were to say specifically for collaborative robots itself, um, we don't really need someone who has a very high skill level to troubleshoot for maintenance issue. In fact, I believe most of the collaborative robot brands that are selling in Malaysia, usually when you buy the robots from them, they will always offer a request for training. It means they offer to request to train your engineers or your technicians in how to operate the robot, how to troubleshoot the robot, and how to maintain or clear some of the errors for the robot. So that is my answer for that.
Mr. Vincent, moving on, which safety standards apply here? Is it ISO 10281, or is it ISO or TS 18066? And what do they practically change?
Okay, to answer this question, I'm going to take out one of the brochures of one of the robots so that we can see exactly what is the safety standards is used. Because a lot of the times, the information we get from all these robot sellers is that they mention they are compliant to ISO, but which specific ISO, then let's have a look and see whether we can find that in here.
Mr. Vincent, you want to share your slide?
Wait, let me try to search for this specific information. Or perhaps maybe I can come back to Mr. Patia, is it? Or I can come to Patia
Yes,
regarding
Patia.
this question. Yeah. Maybe I'll come back after this webinar is over on that.
Thank you. Mr. Patia, the presenter will contact you after the webinar. Okay, moving on. For the no collision cobot safety, by creating an invisible so-called safety zone, doesn't it defeat the purpose of Cobot, where the target is to safely working alongside with human?
Yes, thank you very much, Mr. Haikal, for this question. That's exactly the point that I was trying to make. Because if you look at industrial robot makers like ABB, KUKA, Yaskawa, they would always want to promote these safety-like sensors, say, oh, this is how we are able to implement safe working zone environments. And like you correctly pointed out, the whole point of the cobot is for it to work safely with human next to it. That's why I mentioned there are generally two broad methods. One is the traditional method where you put the safety light curtain and people will question, then what's the point of a cobot then, which you have correctly pointed out in this case.
Thank you, Mr. Vincent. Moving on. How do speed, payload, and tool choice affect safety limits?
Okay, so this is a very good question. Now, in terms of speed, imagine if your robot is moving at a very high speed. For it to stop, the braking force required is very high. And for objects that is moving with high speed, if it hits something, it is already a lot of force in the collision itself. So definitely, if you have a much higher speed, the force during impact will be much higher. Same thing goes to payload. Because if I recall correctly, force equals to mass times acceleration. So acceleration is on the speed and the mass is on the payload. So if you carry a heavy payload and you're moving fast, there's a lot of energy in that collision. So even if you hit something, it's going to be a very major accident, right? In terms of tool choice, this is very subjective because if you design a tool, any factor that has blunt surfaces all around, then definitely one might argue that it's a bit more human friendly, because it will not penetrate, it will not cause bleeding, it will not easily cause catastrophic injury, right? But some of the times when we design the grippers, we may need a little bit of a sharp tip in order to grab an object, or you have a sharp edges because of the machining when we make the gripper itself. So these are things that we need to consider when we need to consider for safety when it comes to using collaborative robots.
Thank you. Next question. How sensitive are cobots to layout changes of floor vibration or wet or chemical operation environment?
Okay, thank you for the question. Now, in terms of layout changes, collaborative robots have a huge advantage. I'm assuming your layout change, it means you change how the robot is being placed, or you change where your machine is located. Because collaborative robots, they are much more lightweight. The whole robot is much lighter weight. The size of the controller is also much smaller. So oftentimes you would see people put the collaborative robot on a trolley with the robot controller and a power supply on the trolley, and you can move the collaborative robots around, right? In terms of floor vibration, provided that your how do you say, the floor, provided that your robot is securely mounted onto the ground, if the vibration is not too bad, and if you didn't set the robot to be the most extremely sensitive, it will have no impact. There are some cases in stamping line. You imagine people like those Produa, they have those huge metal stamping line, 500-ton stamping line. If you go into those environment, you can feel the ground shaking every time the metal stamp. And if you put a cobot right next to the stamping machine where it has the maximum vibration, then the chances of the robot falsely detecting collision from the vibration itself will increase slightly, but it's not too bad. We can tune the sensitivity of it. In terms of wet and chemical operations, this is something that collaborative robots used to be a no-go, because in the past, the cobots, they were designed purely to work with humans. They didn't care so much about the IP 60-something rating and so on. But in the last few years, they began to emerge some of the robots which were designed to work in water. In fact, Dobot has a series of cobots that the whole joint 4, 5, and 6 can dive into a water tank to do some things. So this is where the direction of the technology is heading towards.
Thank you, Mr. Vincent. Moving on. We are in cable manufacturing, and there is no cobot in our shop floor. But I'm interested to know how this can replace human operator in terms of cost and the ROI. Do you have a generic formula to estimate how many human can be replaced by installing one cobot?
Oh, wow. This is a very, very big question. It could have been a big 1 hour lecture on its own, how to calculate the ROI. But in a very brief, based on my experience, a very brief way to calculate it is that we need to find out how many operators this one robot can replace. And that depends on what the operator is doing. If let's say you have 2 operators whose job is merely just picking one object and placing it in the tray, and they're doing this all day long, and the object is a bit heavy, so they cannot, let's say about 4 or 5 kg, right? They cannot do it fast. They have to like slowly pick one piece and put it onto the tray. Then in applications like this, one cobot can do the job of 2 people, which will then make the ROI calculation much easier to achieve. But again, this is very subjective to your existing process, to how much you pay your operators, and also to the final machine design. Because again, robots stand alone has no meaning. It cannot do anything on. The robot must always come with a gripper. It comes with a system. It comes with a structure. And how we design that structure and how we design all these control systems and everything, those costs must be added in together for your final system to calculate the final ROI for your particular project. So again, we need to take a look at your site, understand your process, come up with a rough design, and then from there we can calculate what is the rough ROI for this particular project.
Thank you. We hope this answers your questions. Moving on, what type of battery does the Cobot use?
Okay, for this, the robots usually use a small lithium-ion battery, and this battery's purpose is to store the encoder values of the robots. Means that if the robots has been stopped and then you shut down the power of everything, how does the robot remember what was his last position, current position, what is his current setting? So basically, it's more for the electronics of the robots itself, not so much for the robot motors. So actually, it's a very small robot battery. But the battery is usually lithium ion.
Thank you. We hope this answers your question. Moving on, from your experience, what is the most common mistake corrugated carton manufacturers make when selecting their first Cobot, and what would you advise to avoid it?
Okay, this is a very interesting question. I guess this question applies not just for your specific industry, but for most. A lot of the time, the manufacturers, they are very cost sensitive. So they will always want to pick the lowest cost solutions, sometimes without understanding the nuance of your particular process and what are some of the countermeasures you can use when designing the system. A lot of the times when I give a proposal to customers, they will always, it's normal for them to do a comparison, right, between multiple vendors and multiple designs. And oftentimes they would always pick the design with the lowest cost. And why is it that they go for the lowest cost? Why is it they can give the lowest cost? It's because sometimes they remove certain features. It's not so much on the Cobot itself because most brands, the Cobots are more or less the same. It's more on the system design and the process design, which will actually determine whether the project is successful or not successful. So again, to answer your question, I would say it's mostly a very big laser focus on the cost of the project. That is usually what causes it to fail. Sometimes you may have two proposals, proposal A and proposal B. Proposal B may be about 10 to 15% more expensive than proposal A. So a lot of the times they will choose proposal A and then end up the project maybe not so ideal or it's not so successful. Then they blame it is the Cobots issue, but it's actually more of a system design issue rather than the product issue itself.
Thank you. We hope this answers your question. Next, what is the biggest factor to consider during choosing between Cobot and industrial robot?
Okay, thank you for the question. As I mentioned earlier in the presentation, definitely the payload, the speed, and these are the two usually the biggest factor. Accuracy and repeatability, it really depends on what exactly that you are doing. Because as I mentioned, 5-micron repeatability versus 20-micron repeatability is not too much, but for certain applications, that is quite a big difference. So again, it's a speed and payload. If you want to be very high speed, like for example, you want to do picking chocolates from a conveyor line, very high volume, very high speed, definitely you must go for industrial robot.
Thank you. We hope this answers your question. Next, can the Cobot handle multiple product size or SKUs?
Okay, thank you for the questions. Simple answer, yes, the Cobot can handle multiple product size and SKU. Complex answer, the long answer is it depends on how you design the machine and how you design the gripper. Some customer, they have one conveyor, then they got many different sizes, and then they said robot can only have one gripper to pick all the different sizes. Is it possible? Yes, it's possible, but your gripper will be very complex, very heavy, and may have many complex mechanisms. Or they may suggest you may have a tool changer, means that your robot will go to one place to change the tool automatically. So if it's a big size object, he will change to a big size gripper, a small size object, change to a small size gripper. But that will incur additional costs. It will incur operational complexity. And we have to really study the process to determine what is the most suitable way to solve that particular problem. So again, it's not the cobots issue, it is the system design issue that we have to make sure we propose the thing that works.
Thank you. Next, what is the suitable cobot for vision inspection system?
Okay, for this question, is a bit broad. Usually, most collaborative robots can easily integrate with their own vision systems or with third-party vision systems. So let's say, for example, if you are using Omron TM Cobot, they usually sell with a built-in vision camera on their Cobot itself. But if let's say let's say you're using a Kian's vision inspection system to check for QC and defects, or maybe even for orientation, then we can integrate them together. So to answer the question, generally all cobots can be used with a vision inspection system.
Thank you, Mr. Vincent. We hope this answers your question. Next, what can effectors, grippers, welders, vacuum are supported?
Generally, all end effectors are supported. The question that we should ask is whether some of the cobots, they have I/O pins on the joint number 6. Some cobots, they don't have I/O pins. What this means is that if let's say I am using electrical gripper, right? I may put the I/O through the I/O pins in joint number 6, then the wire will run inside the robot and out through the controller. So that way it looks very neat and tidy. But if let's say you need to use pneumatic grippers, right? You need to have your pneumatic hose and everything connected to the gripper. That's where the cabling will run outside of the robot. So this is where we have to keep in mind, because if we didn't tie these external cables properly, over time, all the robot motion will cause this cable to break and fracture, and that may be a point of failure.
Thank you. We hope this answers your question. Next, I would like to ask whether second generation collaborative robots are more robust in terms of joint durability compared to the first generation models. Based on our experience, many first-gen Cobot tend to develop joint failure after around 5 years of operations. Has joint longevity have been significantly improved in the newer generations?
All right, that's a very specific question and I like it. Simple answer is that the manufacturers still will promise 40,000 hours mean time before failure. So if we were to run 24/7 operations, more or less 4 to 5 years, so even the second generation Cobot, they are rated to perform at that level.
Thank you. We hope this answers your question. Next, what is the correct emergency response for a battery fire involving the Cobot?
Usually, so far, I've never heard of cases of these battery fires inside collaborative robots, because again, the batteries being used are very small, and they are not like those EV fires kind of things. But frankly, I've never seen any cases like that, so I don't really have a solid answer to answer that question. Perhaps if we were to read through the safety manual, the safety precautions, it may give us some ideas on how to handle it. Based on my reading so far, I saw they just said, just disconnect the robot from the battery. But of course, the question is that if the battery is already on fire, how are you going to go into the robot controller to disconnect it, right? So yeah, they didn't really put that much detailed answers in the manuals itself.
Thank you. We hope this answers your question. Moving on, may I know what is the factor that may affect robot precision? Is it noise, humid, dust, or
Um, For this question, there are two things. One is that the robot's own precision itself. So for first generation of cobots, their rated repeatability and precision is about 50 microns, 50 microns. Second generation, they improve it to about 20 microns, 20. And then we also have to talk about the gripper mechanism itself. So you imagine if I'm using a pneumatic gripper. Pneumatic gripper, there is some tolerance between your maximum open and your maximum close. So then we also have to consider the accuracy and the repeatability of the gripping mechanism itself. So those two things will impact the robot precision and also the base, how you mount the robot. If you mount the robot on a base which is not really secure, over time the base will warp, then that will change the accuracy. Noise, humidity, and dust will affect the robot's long-term lifetime. How do you say it? It will affect the reliability of a robot. So imagine if you have a cobot working in a very dusty environment, and your robot controller is kept outside in the dusty environment. Over time, the dust will go into the robot controller, clog up all the fans, and cause some overheating, and that will be quite troublesome. Same thing for humidity. If water vapor seeps into the robot controller, that's where you will have a lot of issues in terms of the spare parts and maintenance. But noise, no issue. Noise, there is no effect.
thank you. Moving on. Collaborative robot, can it be upgrade the safety brake from pin to magnetic?
Unfortunately, no, because these robots, when they were designed, it's like totally different technology. It's like we're trying to compare internal combustion engine and EV. Yeah, both are cars, both have four wheels, but inside the build is totally different. So we cannot upgrade it unless you replace the robot itself.
We hope this answers your question. Moving on, in your experience, what battery-related failure or near miss should new Cobot users be more concerned about, and how can we prevent it?
I think on the near miss side, a lot of the time when people work with cobots, after some time working with cobots, right, they feel too comfortable. They let their guard down too much, They didn't clean the workspace properly, or they begin to put their hands in positions which were not supposed to be there. Then that's where the chances of the accidents occurring will increase. I'll give you one example. Imagine a CNC machine, like in the video I shared just now. The robot will pick the parts and put into the CNC machine, right? Yes, the robot can stop when there is a human hand inside. But now I change the scenario. Imagine now I need to change the chuck inside the CNC machine. I have to stop the entire machine first. Only I can go in to change the chuck. But if let's say some people they are too comfortable or they're not aware, the whole robot machine is still running, but I go and put my hand to change the chuck inside there, then that is where the risk of near miss or even accidents can occur when using this kind of collaborative robots.
Thank you. Moving on. Which cobot is suitable for cutting edges of vacuum-formed plastic objects in place of NC router machine? Is it difficult to program for different shapes? Roughly, what is the cost for objects up to 2 meter equals to 1.5 meter? 2 meter. I don't know what size is this.
By
Is
two,
it?
2 by 1.5,
Yeah,
2
yeah,
by
yeah.
1.5. Okay, understood. Okay, for this case, we have to sit down and study your application because there are too many unknowns. For example, your plastic form objects, what kind of cutter are you using? Do I have to put a force for the cutter to cut through? How fast Do you need the cutter to cut through the program? How many different models do you have? Because I've seen applications where this is done using Cobot and industrial robot. As I've shared earlier, if you have high volume, low mix, high volume, very often industrial robot is a better solution because it's just faster. You can get your ROI better. But if you are very high mix, every month there is new model, just so many models you have to do. And if let's say your production output is not really high, then you can consider using a collaborative robot. But again, very, very subjective. The cost also, I cannot give you any indication. You have to see what is the process you're doing, how the final machine looks like. Then only we have to study in detail. We can only give an answer after that.
Thank you. Moving on. If our production has too many shapes, too many types of items, each item's shape and size were different, but the quantity was low. Can we use Cobot? Since one process will have a lot of changes in the motions, reach distance, and also movement, can one Cobot have many programs inside for different items?
Okay, thank you so much for the question. The simple answer is yes. Cobots generally can store up to 100 different programs. And we can trigger these programs based on either a vision inspection system or manual key in through a touchscreen. Or now I'm running this product model, for example. So can it be done? Yes. Is it easy to do? Again, it depends on the system design, how we design the gripper, how we design the process, how is your input materials coming in? Is it on a conveyor? Is it stationary? So all these factors to me, are the much more challenging questions that we have to address. And if we can address those, then Cobot definitely is no issue.
Thank you. We hope this answers your question. Moving on. Which Cobot can do 7-axis? The added axis is the base conveyor movement.
Okay. Generally, all robots can do 7-axis. The question we should ask is that how easy it is to integrate the 7-axis. What I mean by this is that sometimes the 7-axis is controlled by a PLC control. Means the PLC will control where is the movement of the 7-axis, and the robot just control the 6-axis on its own. So in this scenario, we need to do a lot of program handshake between the PLC, the axis, and the robot, which can be a bit complicated. For industrial robot, this is very, very common application for industrial robot. People like ABB, KUKA, Yaskawa, right? They already have a pre-built library to adapt to 7-axis. So for them, 7-axis integration is relatively easy and relatively straightforward. For cobots, we need to do a little bit more fine-tuning, like a little bit more work on the programming side in order to cater for the 7-axis.
Thank you. Next question. What are the biggest real-world pain points for Cobot users today?
Well, I guess based on my experience dealing with the end users, the biggest pain point that they faced so far is that they are not able to fully utilize the full extent of the capabilities of the collaborative robots. Each different brand of cobots, they have their own unique features, and very often they just use it for some simple pick and place, simple assembly, or they face certain issues which actually can be overcome by features within the robot itself, but they didn't realize that such features exist, and then they always blame that, oh, the Cobot is bad, the feature is not good, it's a terrible product. But actually, it's much more beyond that, right? It is really depends on how we design the system, how we design the process, and how we use the robot to achieve the goal that you want.
Thank you. Next is, what's the realistic lifespan of a Cobot in a 24-hour production environment?
Okay, so this question was actually asked by actually shared by the previous attendee, usually about 4 to 5 years before you begin to see some of the joint failures. Because as I mentioned, the manufacturers, they will rate the performance between 30,000 to 40,000 hours MTBF. So if you divide that by 24/7, it's about 3, 4, 5 years, depending on how heavy you use the cobots.
Thank you. Next, can the Cobot interface with the building fire alarm system?
Okay, interesting question. The only requirement is that the building fire alarm system can give me any kind of communication signal, whether it's by Ethernet or by I/O. As long as you can give me the signal, then if your fire alarm system is ringing, then you can trigger the robot to stop. That one is no issue.
Thank you. Now, I would like to remind again to all participants to please kindly complete the feedback form by scan the QR code as displayed in the slide, or you may click the link that is being shared in the chat box. This is to allow the presenter to share a copy of today's presentation documents. For those who would like to ask questions to the presenter, you may do so by typing in your questions in the Q&A box in the control panel below. So while waiting for more questions to come in, Mr. Vincent, do you have anything final to add after your presentations today?
Yeah, so I guess I've been sharing this throughout the entire presentation itself, and it is the fact that whenever we want to implement collaborative robots in the manufacturing environment, oftentimes it's not just the product, it's not just the robot itself, but we need to consider how we design the machine, how we design the grippers, and how we design the process flow, because that will have a greater influence on whether the project is successful or not successful. You can buy the best, most branded product in the world, but if you use it wrongly, the project is not going to work. So we really need to sit down with you, engage with you to study and to understand your process, to understand your needs. And from there, we can be able to give out a proposal that actually makes sense in terms of being able to achieve what you want and being able to be within the price point where you can meet your ROI.
Thank you. We have another new questions coming in. Can we upgrade the job memory like 10K or more? That is the first question. The second is, if a job like an assembly job that maybe one Cobot can't do it alone, can customize a set of Cobots using 2 or more Cobots to cooperate to conduct the assembly job.
Okay. So I think the question by Wei Jiang and Muhammad Hafiz is almost the same because they're asking about multiple Cobot collaborations. So the good thing is that for all collaborative robots, they can communicate by Modbus TCP or TCP IP, and these robots can actually talk to one another as well as talk to the PLC. So it really depends. Simple answer is yes, they can all talk to each other to do a sequential or synchronous process at the same time. How to do that? There are multiple ways, whether we can have a PLC as a master to give instructions to all of the cobots. Then the PLC will have to determine what is the process flow, or the cobots can talk to one another by sending message over the internet. Okay, I'm done with this step. Now you can do the second step. And while you're doing the second step, I'm going to do step 3. You can do this kind of a synchronous motions. Also, the question from Weijiang, can we upgrade the job memory like 10,000 or more? This one I have to check because different cobot manufacturers have different ways to achieve this high number of recipes or robot programs. So it depends on how you want to implement it. I have to understand your process further as to why you need 10,000 models. Because for some cases, in one program itself, I can use the one program to cater for, let's say, 5 models. How I do it means that in the program, it will be very long. I have an if case. If my input one is high, I run step ABC. If input two is high, I run DEF. If input three is high, I run so on, so on, so on. So within one program itself, I may have different motions depending on what is the input given to me, right? So maybe that way I can even expand my number of models way beyond the 100 programs I shared earlier just now.
Thank you. Sorry, Mr. Vincent. So for Encik Muhammad Hafiz, so this consider the answers for him also?
Yes, because they are the same question with the previous one.
Okay. Encik Hafiz, we hope this answers your questions. Moving on, what is the nominal range of weight that can be handled by the cobots?
So the smallest cobot in the market right now, you can buy it, the maximum payload is about 3 kilograms. Then they typically go from 3 to 5, 7, 10, 12, 16, 20, 25, and 30. Some brands have more range, some brands have less range. It really depends on what on the robot manufacturers they decide what is the specifications that they want to sell and produce. But generally, it's from 0 to 30 kilograms.
Thank you. For anyone who have any questions, you may type in your questions in the Q&A box below for Mr. Vincent to address them.
Perhaps can I share something, Ms. Fana?
Yes, Ken.
Yeah. So if let's say you guys have any of you have a potential projects that you would like to implement these collaborative robots, feel free to reach out to APulsar or to reach out to myself. We will be more than happy to come to do the site assessment, understand your process, and to give you the corresponding proposal. For APulsar, we are a distributor for the brand called Dobot, Dobot. But of course, in this presentation, I'm sharing more on the applications in general rather than promoting one specific brand. So, if let's say you have anything that you want to know more or you want to study, feel free to reach out to us. We'll be more than happy to assist you.
Thank you, Mr. Vincent. For those who have any further questions or you would like to know more about cobots that is being presented by Mr. Vincent, you may reach out to him. Okay, we will take this one last questions. Do you have a support in Penang, Johor, or Sarawak?
Answer is for us in APulsar, we have support. We will support through our partners based in Penang, Johor, and Sarawak because as APulsar, we are based in KL, but we have all kinds of machine design partners in Penang, Johor, and Sarawak.
Thank you, Mr. Vincent. So we have come to the end of our sessions. So just one last reminder, for those who haven't answered the feedback form, you may do so by scanning the QR code as displayed in the slide, or you may click the link that is being shared in the chat box to allow the presenter to share a copy of today's presentation documents. Without further ado, we would like to end the session today. For those who have any other questions after this, you may contact Mr. Vincent. FMM team will be sharing his contacts in our thank you email, which will be shared after this session. So without further ado, I would like to thank you everyone for joining us today.
Question from Kim Wong, is it? He raised the hand.
Oh, okay. Mr. Kim Wong Lim, sorry. Okay. If you have any questions, yes, if you have any questions, you may key in the Q&A box below. Okay, I think no, but if anyone have any further questions, you may contact Mr. Vincent. His contact details is as shared in the slide. FMM team would like to thank you everyone for joining us, and also thank you Mr. Vincent and also APulsar. And we thank you everyone, and we hope we can have APulsar again with us to share more on Cobots. So thank you everyone, and have a great day ahead.
Right. Thank you everyone for your time as well.